And we'll talk about solutions in this chapter. And let me tell you a story. This happened on August 22nd, 1986. People living near Lake Nyos in Cameroon, West Africa. Unfortunately, from this lake, a large cloud of carbon dioxide was expelled and killed lots of people and lots of other animals. And people surviving said that there was a smell of rotten eggs, felt warm, and then losing consciousness. So, and there was a similar tragedy in Lake Manaun, just 60 miles away. So what happened was a massive discharge of gas, in this case mostly carbon dioxide. So it was a volcanic crater filled with water, and something about the Earth, we get our atmosphere from internally. So the volcanism of our planet, one of the reasons why we have an atmosphere and a relatively thick atmosphere looking at other celestial objects. And this concentration of carbon dioxide built up, and then it got to the point where a bunch of the carbon dioxide escaped. The bubbles, the solution, we'll talk about the solutions in a bit, caused carbon dioxide to leave it, and then release carbon dioxide bubbles, and then these bubbles went and then displaced oxygen. It says displacing air, but I mean specifically the oxygen, and it killed a bunch of the people. So they have changed this by finding, by adding some vents. So this way we're not going to have a repeat of this tragedy going on. And so this is, we have done what we can to try and stop this. And so here, for instance, is the geyser there. So with that interesting introduction, let's talk about what solutions are. Solutions are homogeneous mixtures, and it means that there is two or more substances that are uniform. And actually, most of the liquids that we see every day are really solutions. Like, for instance, the ocean. The ocean, well, assuming it's not like a clear ocean, the turbidity, if it's a mixture of things, you could say it's a heterogeneous solution, but most generally speaking, ocean water is a homogeneous solution. So other ones, for instance, blood plasma. I mean, for blood plasma, you have to remove like the platelets and the red blood cells and various other things. And but blood plasma is a solution. And although we mostly talk about solutions as liquids, at least their primary phase being liquids, you can have liquids, gas, and solid solutions. So there's two main components to a solution. The solvent, that's what is doing the dissolving, and then the solute or solutes, because there can be more than one. So, and the solute is what's dissolved. So solvent does the dissolving, that's what's the most of it, and the solute is what is dissolved. So in a liquid solution, we say that the solvent, the liquid that's doing the dissolving, so often frequently water, even though if there is more than 50% by mass, we still consider water to be the solvent. And water is relatively abundant here on Earth, and it's a very, very common solvent, if the most common solvent, at least here on Earth. And the solutions that make that, we call it aqueous solutions. There's other solvents that we use in laboratory, industry, like hexanes, for instance, or you can use gasoline, you can use kerosene. Those are non-polar solvents, but we typically use water. Water is a very, very common one. So this table here shows the different types of phase, different types of solutions. So start with the gaseous solutions, and you can have gas and gas. So air. Air, for instance, is a solution. It's mostly oxygen and nitrogen, and if you will, the nitrogen would be the solvent there. Although we because of gases, the nature of gases, we don't really necessarily use the term solvent, because solvent implies there's an interaction, and in a gas, especially this temperature, there's pretty much, and using the ideal gas law, at least the kinetic molecular theory, there should not be any interaction. So we typically don't use the word solvent with gases. Although liquid solutions, you can have gases dissolved in liquid, just like the carbon dioxide with the lake example we talked about at the beginning of this chapter. You can have two liquids, like alcoholic beverages are essentially liquid-liquid solvents. And you can also have solids dissolving in liquid, like seawater. You can also have solid solutions, so like alloys. Alloys, here is brass, 14 karat gold, 12 karat gold. You could even argue there's liquids dissolved in solids. When you put mercury can absorb into certain metals to form a solvent phase there. But I mean, yeah, this is just generally speaking here. Those are relatively rare. So some common polar solvents, and this is the molecules are polar. So polar tends to mix with polar, nonpolar tends to mix with nonpolar. Polar and nonpolar tend not to mix together. There are some exceptions. Ethyl alcohol, ethanol, that tends to mix with both polar and nonpolar. But generally speaking, things either go in the polar or non-polar camps. And the reason why they don't mix is because of intermolecular forces. So the polar molecules have dipoles, permanent dipoles, and actually the nonpolar molecules get in the way of those dipoles, so the polar molecules push them out of the way. So it's actually the people think that oh, gasoline hates water. Oh, gasoline loves water, but water does not think that gasoline is attractive enough, so it pushes it out of the way. So how do things dissolve in water? Well, it has to do with energetics. So and generally speaking, if the attraction between the solvent, what's dissolving, and the solute, what is being dissolved, if the attraction between these is greater than the attraction with itself, then the solution forms. So if you see here, for instance, here with sodium chloride, and you can see here that you have the sodium chloride in that matrix there, the matrix being the crystal structure. But you can see there that 6 water molecules surround both the chloride and the sodium ions. And the idea is that these 6 attractions, so these 6 bondings between, well, I guess it would be 12 if you count the times 2. The attraction between the 12 water molecules and then each of the ions is greater than the attraction between themselves. And then because of that, the solution forms. If you remember from earlier chapters, we're talking about solubility rules, and one of the things I said that for things to be soluble, you have to have big ions and small charges. And so sodium chloride is an example of a big ion and a small charge. If you start having more positively charged things, they tend not to dissolve in water, just because of this very fact that then the attraction between the water is not greater than the attraction for the ions between themselves. And so therefore they don't dissolve. But sodium chloride is a relatively weak ionic bond, so it can dissolve in water. And so the water molecules then surround it, and now we have a sodium chloride solution. And we'll talk about this in a little more. Sodium chloride is also known as an electrolyte. So it means that this solution can conduct electricity. So pure water, does not tend to conduct electricity very well. So solubility, this means how much can dissolve, and we usually do it in grams. Grams per 100 milliliters, 100 grams of water is very common. For instance, so sodium chloride is 36 grams per 100 grams of water. And if you've ever made a pure brine solution, it is difficult. There is so much salt that dissolves in the water. If you ever want to do this at home and see how much salt you can get dissolved in the water, it's a lot. It takes quite a bit of time. And once you get to the point in time that no more salt will dissolve in water, this is called a saturated solution. So this no more can go in, and that's a saturated solution. So that's what saturated means. Anything less than that, though, is unsaturated. So unsaturated means you do not have the maximum that can go in. If you add more solute and it more dissolves, then the solution is unsaturated. Under certain circumstances, you can do supersaturated solution, which is well, there's a couple ways you can do this. Typically speaking, when you heat up a solution, then you can argue that's a supersaturated solution. Well, then when it cools down, it'll turn into a supersaturated solution. Then it's just ready to crystallize at that point in time. So then when this happens, it forms a precipitate, which can be a lot of fun. And I'll talk later about making rock candy. That's how you make rock candy. So these are supersaturated solutions are really kind of they're metastable, sort of stable. So they just need a little kick, and then they collapse. So if it's like with gases, it means the gases all escape. If it's an ionic compound dissolved in it or other compound, then it'll crystallize and all falls out. It's kind of fun. These are fun to play with. And the example, the beginning of the chapter example is an example of a supersaturated solution. So mention more about, I already mentioned this about the solubility rules, that the bigger the charges and smaller ions means less solubility. Some molecules, like sucrose sugar, sucrose has a lot of OH groups on it, and then they can hydrogen bond with the water. So sugar is very soluble in water. So nonpolar solids, though, typically these do not dissolve in water. So things like fats, these do not dissolve well in water, and aforementioned because of the nature of the intermolecular forces. So electrolytes and non-electrolytes. Electrolytes are solutions that conduct electricity. So there are also solutions that are non-electrolytes, so sugar water. So we already mentioned sodium chloride, salt being electrolytes. You see these in sports drinks. So what does it mean if it has electrolytes? It means it has salts. Non-electrolyte solutions, though, just have molecules. So like sugar solution, example of one. Alcoholic beverages, although it's not necessarily a solid, but that's another example of something that's a non-electrolyte. Generally speaking, solubility increases with temperature. The reason for this is because of something called Gibbs free energy. And the Gibbs free energy is the enthalpy plus the temperature times the change in entropy. And the entropy is the disorder. So we're not going to cover this deeply into this class, but if you're wondering why this rule is generally true, when you increase the temperature, the entropy term can overcome the enthalpy term, and then more things dissolve. So this is a general rule, and you see actually sodium chloride is pretty flat, but a lot of other salts, they increase quite a bit. So with that chart there, and if you look at this chart here, the y-axis is the amount of the solubility in grams per 100 grams of water, and the x-axis is temperature, and you can see, except for cerium sulfate, it really increases. So we do a purification technique called recrystallization, and this is kind of fun. When you take things, you heat it up, and then you elevate the temperature, and then you cool it. Typically in the lab, you would take like an Erlenmeyer flask, and then you heat it up, and then you stick it in an ice bath, and then you wait, and then it forms a supersaturated solution, and then either it just goes by itself, but what's more fun is if you take a glass stirring rod and you scratch the bottom, and then you get this whole solution crystallizes down, and you get a relatively pure product because, among other things, you can filter the warm solution to get rid of anything else in there. And then when you form this precipitate down, it tends to result in a purer solid. So like I said, it's a purification technique. And if you want to do this at home, you can make rock candy. So you can make a very supersaturated sucrose solution, and then you take that and you can let it cool. So you can put some strings on there. I've done this also with like bamboo skewers. That seems to work kind of well. But you can also like dangle strings in the solution, and then you can form the rock candy. And also, I usually get rock candy growing on the side of the container too, and then you can scratch that off. So it's a fun thing. You can also, if you want, you can add flavoring to it as well. So rather than just eating pure big sugar crystals. So yeah, that's rock candy. So let's talk about gas and liquid, especially water solutions. So carbon dioxide, for instance, can dissolve in the water, and there's not just carbon dioxide. Carbon dioxide. There's other gases that go that react with water. Well, not react. Carbon dioxide actually does react with water. Ammonia is another one. Ammonia is very soluble in water, but oxygen, for instance. It does not react with water, but it does dissolve a little bit in water. But dissolved oxygen is very important because that's what a lot of marine life use for that. Also, nitrogen dissolves in water, and you can get things like the benz, which we've mentioned before. So carbon dioxide is more soluble in water than oxygen and nitrogen, and the reason why is because actually it reacts. There's a chemical reaction that it forms something called carbonic acid. And you can get other gases that similarly react with water to form other compounds, and so their solubility generally can go up. And but we also use this. We use this in our breathing. So our bloodstream, actually our blood plasma itself, carries the carbon dioxide, and then we exhale it through our lungs. So it goes both ways. We'll talk about that in equilibrium next chapter. So there's a temperature dependence, and the temperature dependence is the higher the temperature, the lower solubility. So this is opposite of the solids and liquid. But I mean, for gases and liquid, the higher temperature means less solubility. And the same reason, the Gibbs free energy, the T delta S term, the temperature times the change in entropy, and gases have higher entropy than liquids. And so the higher temperature drives the physical process more towards having a gas and a liquid, but not a dissolved liquid. So that's the reason why this is going that way. So hopefully, telling you the real reason helps you understand this. And so maybe you understood that when you are if you notice that if you put soda in the fridge and or soda at room temperature, if you open up the soda in the fridge, it doesn't like fizz as much and as quickly as you do with warm soda. So we can also describe this using something called Henry's Law. And Henry's Law is something called a semi-empirical model. It's a really straight and easy model. It's just the solubility of the gas is the pressure of the gas times the Henry's Law constant. And so we've just dumped it all into the Henry's Law there, and it's like I said, a semi-empirical model. Henry went and took a bunch of data and figured this out, so it's a straight shot. And but also the consequence of this, well, if you increase the pressure above the liquid, then more stuff dissolves, and that's how we make soda. So that's one of the ways you can make soda. I've made my own soda. It's kind of fun. Like I did something called a ginger bug, where I took some organic ginger root and ground it up just using a cheese grater, and then I fed my ginger bug with sugar and stuck it in the fridge and made my ginger bug pet. And when the bacteria that's in there, it generates carbon dioxide, and then you can take the ginger bug and you can put it in some water and give it more sugar, and then give it some typically some acid like lemon juice or orange juice, and you can make your own ginger ale. And it really made a lot of fizzy things. So, but I put a normal soda bottle in it, and I put it under a lot of pressure. So that was some really fizzy ginger ale that I made, and of course you can do it the natural way, in your home, but they can do this in a factory, like in a Coca-Cola factory. You can go and you can just turbocharge it with CO2, or you can do this at home if you have a carbon dioxide tank. You can make your own seltzer water. So, but then Of course, if you notice that a like aluminum can, for instance, is pressurized, right? So if you shake it up and you puncture it, you can hear the or even if you open the cap, you hear the sound of the gas escaping. So the pressure is released, and now when that pressure releases, the carbon dioxide is less soluble, and it bubbles. So let's start talking about concentration. So what I like to think about is like orange juice. You know, you go to the grocery store and you get that tube of orange juice concentrate. Well, what does that means is like all the orange juice goodness is concentrated in this tiny tube, and you put it into a pitcher and you dilute it. Now you have regular orange juice. So that smaller tube of orange juice goodness, as we call it, concentrate. There's more stuff. So concentration means amount per volume. So amount per volume. And so a concentrated solution means that you have a lot of solute to a relatively small volume, and a dilute. So concentrated is strong and dilute is weak, which means you have less. You have smaller amounts. So I think you probably have used these colloquially, though, so these probably make more sense. So there's a couple ways we can quantify the concentration, which is amount per volume. And what's very common in many other solutions is mass percent. So and also maybe percent by volume too is another one. We do that alcoholic beverages. So proof, for instance, is just 2 times the concentration by volume. But mass percent, so for instance, vinegar, for instance, is typically 5% by mass acetic acid. And if you'll see that if you read the labels on vinegar bottles, it'll probably say 5% acid or something like that, or on there, and that's percent by mass. And so that's just the mass of the solute over the total mass of the solution times 100%. So, and we use this mass percent for a lot of things. Body fat percentages, for instance. I mean, people say, oh, what's your body fat percentage? Well, that means how much fat you have over your total mass. And so the same thing with a solution, the mass of whatever you're looking at over the total. So, and we can go further. So mass percent is also really parts per 100. But if you want to, so like you take a fraction, you multiply 100, it gives you percent. If you take the fraction, multiply it by a million, you get the ppm, parts per million. If you take the fraction, multiply it by a billion, you can get the parts per billion. You can for even smaller things, you can get it multiplied by a trillion for parts per trillion. So, I mean, the ways you can go can keep on going up with the smaller fractions, I guess. So, but you've probably seen parts per million, parts per billion for certain things like that are in small quantities, like the concentration of carbon dioxide in the atmosphere, or the acceptable amount of lead you can have. For instance, these are shown in relatively small numbers, and that's why we need the parts per million. So this one's pretty easy. For me, I see percentages as a fraction. So if you recall some of your math training early, a percentage is just a fraction. And let's use an example for this. The water sample was in the bottom of Lake Nyos was 8.5% carbon dioxide by mass. Determine the mass of carbon dioxide contained in 28.6 liters of the water. Assume the density is 1.03 grams per milliliter. So to do this, we're going to do dimensional analysis. We're going to start off what we know. We're going to work our way over to the answer that we need, which is mass of carbon dioxide. So we'll start off with the amount of solution here. So 1,000 milliliters. I'm sorry, we could divide. A milliliter is 1,000 liters. So, I guess you divide by that, so you multiply by 1,000, and then you. For that step, if this book shows, I would have done 1,000 milliliters per liter. I wouldn't have done it that way. I like multiplying more than I do dividing, although it does make sense. But then, so 1.03 grams per milliliter, and then this is the concentration, which was given there in mass percent, and then we're left with 2.5 kilograms of carbon dioxide. So that's the the solution there. And if you've noticed the second step there, I mean, I would do 1,000 milliliters per liter, but I mean, this way does make sense. And as long as you put your number in the calculator correctly, you should be fine. So let's talk about how chemists do things. We more commonly in the chem lab, we use molarity. Molarity is defined by moles of whatever, typically the solute, but I mean, you can do, it's like the concentration of water, for instance, is 55.56 molar, but the molarity is the moles of whatever you're looking at over the liters of solution. And it's the total solution, though, not the solvent. So when you do this, you look at a total volume of the solution. And for instance, if you want to make a 1 molar sodium chloride solution, you take a mole of sodium chloride, which is 58.44 grams, and then using this volumetric flask, you can put in exactly you can put it up to the line, and then it dissolves. And then sometimes you have to come back and make sure nothing has evaporated, or maybe the after it's dissolved, the line's gone down a little bit. So you check the line, you can add a little more liquid, and then you get a 1 molar solution. So that's how you make a 1 molar. So it's 1 mole per liter, and it's the total solution. So let's do this example here. Calculate the molarity of a solution made by putting 15.5 grams of sodium chloride into find a total 1.5 liters of solution. So we're given the mass of sodium chloride and the total of 1.5 liters of solution. What's the molarity? Well, that's moles per liter. So molarity is moles per liter, so we got to figure out the number of moles of sodium chloride and then divide it by the total volume of the solution. So moles of sodium chloride is going to be 0.265 moles of sodium chloride divided by the 1.5 liters of solution, and we get 0.177. We get that capital M. Capital M means molar. You can also write moles per liter. So typically when you see this in chem lab, or you'll have the capital M and then you say what it is, NaCl, that tells you what the concentration is. Let's use molarity in some of the calculations. Determine how many grams of sucrose are contained in 1.72 liters of a 0.758 molar sucrose solution. So we're given a volume of solution and concentration. So concentration is moles per liter, and then we are given the volume of the solution by liter. So if we multiply the concentration by the volume, we're given the number of moles of solution. So, and it's asking for the mass. So we have to use some of the previous things to figure out the molar mass of sucrose. So you already know how to do this using the periodic table. If this has not been given to you, you can use the periodic table for this. So the idea here, we take the volume of solution times the concentration, that tells us the number of moles. Then we multiply by the molecular weight to give us the mass. And doing that, we get 446 grams of sucrose from this. So let's do another example. How many grams of sucrose are in 1.72 liters of a 0.758 molar solution? So it's, wait, I already did this, I'm sorry. Let's do molarity for ion concentration. One thing about ions, sometimes it's a 1-to-1 molar ratio, sometimes it's a more than 1-to-1 molar ratio. It just depends. And why are we doing this? Because we're going to talk about something called colligative properties, where the number of ions matters. So for instance, for sugars like glucose or sucrose, the moles of the molecule equals the moles of particles in the solution. But for ions, this can change. For instance, calcium chloride, this actually has a total of 3 moles. For a 1 molar calcium chloride solution, we actually have 3 moles of particles. We have 1 mole of calcium and 2 moles of chloride. And so looking at this as ionic compound. And this is important because there are certain properties that can change depending on how much stuff you have in there, stuff being ions. So let's use an example here. What is the molar concentrations of sodium ion and phosphate in a 1.5 molar sodium phosphate solution? So we got to figure out the moles of each. And so sodium phosphate has 3 sodium ions, and because of that, we have to multiply the concentration by 3. So 1.5 molar solution of sodium phosphate contains 4.5 moles of sodium and 1.5 moles of phosphate. And the total ions, of course, is 6. So keep that in mind, that you have to add them together even one more step if you're talking about colligative properties. So before we talk about that, though, let's talk about some of the things we do in the lab. And we don't always have solutions just ready to go. Sometimes we have to dilute them, and we have more concentrated forms. We call them stock solutions. Sometimes they're in the big bottles. Sometimes they're diluted to something convenient, like 1 molar or something like that. It's really easy to make half molar from 1 molar. It's really easy to make 1/10 molar from 1 molar. So I like to have those solutions handy, but I mean, you can have just the plain old bottles that are very concentrated also in the lab. So, and there's ways to do this. It's pretty easy. And the formula we use is M1V1 equals M2V2. That's the molarity of 1 times the volume of 1 equals the molarity of the second, volume of the second. And it's really just moles equals moles. So M molarity is moles per liter, and volume is liter. So you're just saying that the number of moles equals the number of moles. And the thing that's different, though, is the concentration and the volume. So we're not creating or destroying matter or number of particles, right? We're just making more dilute. So this one does not apply to stoichiometry. So you have to go straight across, and so do not apply stoichiometry to this equation. So prepare 5 liters of a 1.5 molar potassium chloride solution from a 12 molar stock solution. So we are given, our M1V1 is our original, and we're trying to form we don't know how much of the original. We know the concentration of the first, we know the concentration of the second, the volume of the second. We just don't know how much we need of the original. So do the equation, solve for the unknown variable, plug in the numbers, and we only need 0.625 liters or 625 milliliters of that concentrated solution and dilute it down to 5 liters to have that 1.5 molar solution. So this shows you how you would go ahead and do it, and then you could use a volumetric flask. For me, myself, I probably would grab 2 of these. I'd probably grab a half a molar, or half one and a 1. A half a liter and a 1 liter. I haven't seen too many 1.5 liters of these. But then I would go and then I would fill one with water, fill the other one with a solution. Then I mix them again. So that's probably what I would do personally. But I guess for illustration purposes, we'll just have the 1.5 liter solution there. So let's talk about stoichiometry. When we do chemical reactions here, we still have to keep an idea where the coefficients go, and then track to see where the reaction goes and how much it goes. So stoichiometry is important there, and the whole thing with chemical bookkeeping. So the general idea goes volume of A times the concentration can give you the moles of A, then you get the moles of B, and then you can divide by the total volume to get the volume of B. And so and don't forget, though, that in a chemical reaction you can generate and consume things. So you have to keep track of what's being generated and what's being consumed, and then take that total amount of moles from that and then divide by the volume to get the concentrations. So for instance, how much 0.125 molar sodium hydroxide solution do we need to completely neutralize 0.225 liters of 0.175 molar sulfuric acid? And the tricky part of this one is the balanced chemical equation is that you need twice as many moles of sodium hydroxide as you do sulfuric acid. So looking at the balanced chemical equation there, you have to, so you need the 2-to-1 molar ratio between the sodium hydroxide and the sulfuric acid. So this is going to change the numbers a little bit. And that number then in the middle is the second step here, or the third step, I should say. So we start off with the volume of the solution. So we have 225 milliliters, and then we have the concentration, 0.175 moles per liter. And then we have that 2-to-1 molar ratio. So now we're going to convert to moles of sodium hydroxide. And then we have to divide by the concentration, and you divide by the concentration so that the units are in the right place. And you're left with 0.63 liters of the sodium hydroxide solution. So when you do things like, this is a neutralization reaction, when you do these chemical reactions, you have to keep track of what's going on with the chemical reaction and where it goes. So another one here. So how much 0.115 molar potassium iodide solution will completely precipitate the lead plus 2 ions in 0.104 liters of 0.225 molar lead nitrate solution. So in this case, though, they're similar to the previous one. You have a 2-to-1 molar ratio for the iodide versus the lead, and I say the iodide because that's the net ionic reaction here. It's the iodide is reacting with the lead to form the lead iodide solution. So we need twice as much. So in setting this up, then we start off with the volume of lead nitrate and then the concentration. So now we now have moles of lead, and now we convert to moles of potassium iodide, and now we divide by the concentration again. So this is because of the units. So that way we get the volume of the solution, and that's what they're asking for at the end, is the volume of the solution. So I told you I'd talk about colligative properties. So here we are now. There are two things that happen with solution. There's freezing point depression and boiling point elevation. So let's look at these words and what they mean. Like, I'm depressed, I'm down. So I'm down, I'm depressed. That means that if you add things to water or other liquids, you can depress, you can lower the freezing point. And also, same way with elevation, when you add things, you can elevate, you basically expand the liquid phase. So liquids phase is it's kind of a weird phase. I mean, liquid phase does not always exist, actually. So depending on the temperature and the pressure. Because of that, actually adding this is always say expands liquid phase, because liquid phase in a way for matter is kind of weird. So although we see liquid all the time, the planet's, most of it's covered in liquid water, for instance. So, but generally speaking, liquids are kind of rare. So, but same thing with freezing point. And both of these, freezing point depression and boiling point elevation, are colligative properties, meaning they depend on the number of particles. So the number of particles and the solute. And for instance, I already mentioned colligative properties. If you've ever lived somewhere cold, you can throw salt on snow and it melts the snow, but it only works to a certain point. So you can eventually it gets too cold and salt doesn't work anymore. But then it's a lot easier to deal with liquid water than it is with salt. And you can even do that to make ice cream. So if you want to get the temperature down, it's just cold enough to freeze the cream. So I usually just put it in the freezer. I've made ice cream before, but I have a machine. So we've mentioned molarity, and we use molarity quite a bit. But there's another concentration term called molality. So molality is similar to molarity. They're not always the same. They can be close, but not always the same. Molality is moles of solute divided by the kilograms of the solvent. So this is different than molarity, and it's molality is also using tiny m, and molarity is capital M. So, for instance, what is the molality of a solution containing 17.2 grams of ethylene glycol in half a kilogram of water? So it's moles per kilogram. So we got to figure out, first of all, get the molecular weight of ethylene glycol. And from that, well, we can figure out there's 0.277 moles of ethylene glycol. And then you take that, the moles of ethylene glycol, and then you divide it by then the mass in kilograms of solvent, and you get 0.554 molal. You say the word molal solution. So capital M is molar. This is molal. And freezing point depression, you can calculate this way. The change in the freezing temperature, so delta TF, change in the freezing point, is the molality times the freezing point constant for the solvent. So different solvents have different values of KF. Water is actually kind of low. There's other ones that are really high, especially organic compounds. But for water it's 1.86, and that's degrees Celsius per mole of the solution. So the other thing with this, the most common problem with this is that people forget to subtract at the end. So looking at this problem the most common problem for students in this one is don't forget to subtract at the end. But okay, let's calculate the freezing point of a 1.7 molal ethylene glycol solution. Ethylene glycol, it's antifreeze. It's the stuff that's in your car, the antifreeze. So doing this, we have the delta TF is the molality times the freezing point depression constant for water. So it's 1.7 times 1.86. We get 3.2 degrees Celsius. And we're like, oh, we're done. But don't forget, it's freezing point depression, that it goes down. So the freezing point is now negative 3.2 degrees Celsius. And you can see now, this is why we call it antifreeze. It's keeping it from freezing. So we can see this in other animals. So we've been trying to study hibernation and looking to see how we can hibernate. We're interested in this for a few reasons. A lot of them is space travel, because you're like, oh, we can hibernate the people, and then so if they're going to be, if we're going to have to stick somebody and they have to it takes 100 years to get to a star. Well, why don't we just put the people in hibernation? They can wake up and then all is good. We're looking at this and like creatures like bears hibernate. Not only do they wake up and after hibernation, they haven't lost any bone density and they haven't lost any muscle tone. So we're trying to see if we can figure out how to humans do this. We haven't really quite figured it out yet, but we're getting there. But wood frogs do something interesting. Is right before they're gonna freeze. Actually, their adrenal glands release a bunch of glucose, and then so their glucose levels go up really high in their blood, and then that acts as an antifreeze. And so actually, then the frog just stops moving, and it just like everything shuts down. And then later on in the spring, when it warms up, it warms up and then it hops away. So, and this is done via just good old fight or flight response with the adrenal glands, and it's just similar to like with humans with our fight or flight response, releases a bunch of sugar in our bloodstream, and they don't they don't completely freeze, and so they don't get frostbite, they don't get tissue damage. So this is kind of cool. So we mentioned freezing point depression, and there's same idea, boiling point elevation. And so this way you expand liquid phase a little bit more. I always found this a little depressing that you don't really increase the boiling point as much. It's much easier to, generally speaking, to decrease the freezing point than the boiling point. But it's the same idea. It's really the same idea, except use the KB instead of the KF, and then, I mean, same rules, use molality, get the change in temperature, but then with this one, you have to add it instead of subtract. So what's the boiling point of a 1.7 molal ethylene glycol solution? Same idea. When we apply it, though, we get 0.87 degrees Celsius. And then we have to take this and we have to add it to the boiling point of water, which is 100 degrees Celsius. So we get 100.87 Celsius then for the boiling point of this solution. So same idea as the freezing point, but you add it instead of subtract it. Another thing that is a colligative property is osmosis. Osmosis, and specifically osmotic pressure. And it can cause, if you ever wonder what osmotic pressure is, and it has to deal with when you have two solutions, one that has a very high concentration. And of course, the thing everyone talks about this is trees. So trees have leaves, and trees, essentially what they are water pumps. So trees are really good water pumps, and they have roots that go down, and the trees are able to draw the water from the roots all the way up to the leaves to do photosynthesis. And how are the trees able to do this? They can do this with osmotic pressure. So they put a high concentration of sugar in the leaves and other ions, but it's mostly sugar. And then it can draw the water from the ground all the way up the tree, all the way up through the trunk of the tree to the leaves. And that's why also animals like eating leaves, because they're sweet. I don't know. I haven't eaten. I guess romaine lettuce is kind of sweet, if you will, but I guess I don't eat too many leaves. So, but this can cause other issues. So seawater. So the human body, for instance, tends to be 0.9% sodium chloride solution, and ocean water, generally speaking, it varies, but it's usually about 3.5%. And if for us humans, if we drink 3.5% salt water, this will actually dehydrate us. There are other animals, sea otters, for instance. They have really, really good kidneys. Our kidneys are not as good as sea otters, so we can't drink ocean water and get refreshed. Sea otters can, but we can't. And what happens is actually if we drink really salty things, the salt will draw water out of our blood plasma into our digestive tract. And one thing about humans, we are interesting creatures. We move water around very quickly. So like when we sweat, for instance, that water comes from our blood plasma. So we're very good at dissipating heat compared to other animals, but we're not as water efficient. There are other animals that are much more water efficient than we are. We are water inefficient. So we're fragile that way, but we have some high performance. So we've sacrificed high performance for our efficiency on this. But this is for humans. Of course, osmotic pressure works for all living creatures. Where the osmotic pressure comes from. So if you see this U-tube apparatus, and it's called a U-tube apparatus because it's in the shape of a U, and if you put a semi-permeable membrane, and the semi-permeable membrane means that water can pass through, but the ions can't. And then what happens is that the water will migrate from make the concentrated solution, it will migrate over to form it less concentrated. And then when it does that, the height difference between the U-tube changes. Okay, and then it gets to a point where there's an equilibrium, and then that height in terms of the mass of the water. And so remember, 10 meters of water is the same as 760 millimeters of mercury, which is 1 atmosphere. So you can use those conversions, and then that number there is the osmotic pressure. So that's the whole thing where the osmotic pressure comes from. And like I said, with trees are so good at this, they're able to draw water up from the ground all the way up into their leaves. So the osmotic pressure, it's the pressure required to stop the osmotic flow. So just think about that water going up the trees. And the more concentrated a solution is, the greater its pressure. So that's the idea there. And it's colligative property. It's the number of particles, not the type. And we didn't really do calculations with this, but if you're going to do like boiling point depression, for ethylene glycol, we were using ethylene glycol. It was 1 particle. If you use sodium chloride, you'd have to multiply everything by 2 because it has 2 particles. And if you used iron 3 chloride, it had 4 particles, and you have to multiply it by 4. So keep that in mind with this. So we worry about solutions, and you got to be very careful what you inject into the human body, for instance, or any living creature. So if you have the osmotic pressure that's less than the body fluid, this is called hypoosmotic. And when this happens, these will cause water to flush into the cells. And the reason to do this is then because then there's pressure in the cells it wants to make the concentration of whatever it is, sugar, salt, in the cell to be equivalent to what's outside the cell. And you have to be careful with this because if you push too much in, you can rupture the cell. So then the other way is hyperosmotic. And when this happens, then water rushes out of the cells, and then you have like kind of shriveled cells for this. So, and when we do things like IV bags, we make sure they're isoosmotic, which means that the same amount of concentration as the human body, and that's 0.9% by mass sodium chloride. So you got to make sure that these are isoosmotic. So here's a review of this. Solutions are homogeneous mixtures. Solvent is whatever is the most is. Solute is the lesser component. We have different types of solutions. You can dissolve solid and liquid. And the solubilities, these tend to increase with increasing temperatures. Gas and liquid, these tend to decrease with increasing temperatures, and the reason for this is Gibbs free energy. Solution concentration is amount per volume. There's a couple of ways we can do it. Mass percent is very common, used colloquially quite a bit, and parts per mass, like parts per million, parts per billion. Molarity is moles per liter, used very commonly in chemistry. Molality is moles per kilogram. This is used less frequently, but can be used in certain colligative properties like boiling point elevation and freezing point depression. And we can use this M1V1 equals M2V2. Some people use it M1C1 or C1V1 equals C2V2. Those are the same the same formula. It's just if you want to call it M for molarity or C for concentration, whatever works for you. Colligative properties, these deal with the number of particles, and mentioned that for freezing point and boiling point there, the change, and osmosis we've mentioned there. Here are the learning objectives. The copyright. Thank you again for your attention.